On to our second part is an introduction towards the actual simulation itself. So I'm going to keep the thing that we wrote earlier to remember. You need to always remember this. Should always be there. If you have difficulty memorizing or remembering anything, it's really important that you write this in the exam. Really, I really recommend you. It will really help you a lot if you write this in the exam. So in simulation, we're gonna do a very basic simulation of mechanical systems. So in mechanical systems, for the biggest, simplest example would be I have a boundary, we have the floor, and we have a wall, and we have a mass M, and we have wheels on it, and therefore we say that we connect a spring and a damper. And we're gonna say that the coefficient of friction is equal to 0. So, and we call this also the reference point. Let me use a different color. Reference point, and therefore we say that this point here these are fixed points. Fixed points. So when we have a force, we need to really identify our line of action. So in our line of action, we would say that we have at here 2 lines of action. We have the line of action here, our first line of action, and at the mass, we have our second line of action. Now, it's important to know that your second line of action at this point here is the same if you were to take the line of action over here. Some of the professors may take it here, but I like to take it in the middle of the mass. But actually, the truth is that it's actually more better and correct if you take it at the end of the spring. It depends on how you visualize it in general. So, in our question, it's actually given to us like this, as how I said. And we are given a force F0 here. So, how you usually approach around this topic is that you need to understand that when a force is being pushed into this direction, your spring opposes the force in the opposite direction, and we call this Fc, for example. I call it Fc. And your damper functions just like your spring, and it opposes the force as well. Now, some of you may say, but isn't a damper supposed to oppose the spring and not oppose the direction? Well, my professor said that it should follow like spring, and we could explain more into this, but for me, at the moment, I prefer to just accept it as how it is. So we know that our FD and FD are both pushing and then going against the motion itself. So to write this in a better sense, I will write. So always remember, I'm gonna write like my FC is here. Put it here, for example, and my FD, I'm going to move it here. It doesn't matter if it's top or bottom. It's just important that they point in the correct direction. This line does not equivalent to an equal, so please do not think it of that way. It's only just a line of action, line of reference or line of action. So now that we know that our direction of FD, F0, and FC, we can concur that our FM is pointing in this direction. Now you're wondering, why does my FM point in that direction? So because you have a mass M, and it moves in this direction because of your F0. So therefore you have inertia, which is MA. And you would think, oh, so therefore FM should be in the same direction as inertia. But no. What is actually happening is that your MA must equal to your FM, and therefore they must oppose each other. So therefore, if your and therefore, I made a mistake, and therefore your FM is pointing in this direction instead. So you saw that I actually didn't know the direction of FM. I had to use this to derive. So the simplest way to know is that your FM is always in the direction of your line of action. It does not follow this one, so please don't follow your F0, but it follows your direction, your A, your acceleration. So in here, we are going to say that we have a velocity. Velocity. This one moves at a certain velocity v, and your wall, it doesn't move. We call this w. We could actually, well, in the British sense, we wrote u as initial velocity and v has our final velocity. But in the German sense, they use v for initial velocity and they use w for final velocity. So in further calculation, please do not confuse when you write this as your second or final velocity and your omega has angular velocity. They are not the same thing. Some professors may write it like that, and this one they write it like this. And this could also be mean work. So yeah. So now that we have our v and our w is actually equal to 0 because it is fixed, a fixed point. So from v to w, we say is the difference of v, w. So when we want to solve a question like this, we need to first identify our energy accumulators. Our energy accumulator is the spring and the mass. So we're going to start off, this is our technical schematic of effect. And, oh yeah, there's one thing I need to mention that, so just as a good hint to remember, always remember you start with your F0, and then from there you get your FC, FD, and the final part will be your FM. So after you've done your technical schematic effect, what you want to do is you write your energy accumulators, or energy storages, as I write ES. So in ES, we have our mass. So mass is equal to V equals to 1 over m integration of Fm dt. And then we have our spring, which is, in our spring, we write Fc is equal to 1 over c multiplied by the integration of uc. So using Laplace law, we will then transfer this as v equal to 1 over m times fs, and your integration will become 1 over s. So here it means you get fc is equal to 1 over c uc multiplied by 1 over s. No, this is not u, this is a velocity, so it's v. And when we rearrange this, we write our gm, our mass, or the transfer function of the mass, is equal to v over fm equals to 1 over m multiplied by 1 over s. And this would mean that our input is 1 over m and 1 over s. Our block diagram is 1 over m, 1 over s. And then our input is fm and our output is v. And in here, we say that our GC is equal to FC divided by VC, which is equal to 1 over C times 1 over S. 1 over C times 1 over S. Input is VC, output is FC. So after we have done that, we now going to write our equation of balance. EB. So in our equation of balance is always the sum of input equivalent to the sum of output. It does not follow the direction of the arrows, but your input equivalent to your output. So your input, you have F0, and F0 is and negative Fc minus Fd, and is equal to your Fm. Even if your Fm is pointing the opposite direction, you will still write Fm. So from here, because in this question we were not given what our input should be and what our output should be, but we can know that from this equation of balance, we can draw not a block, our sum. It's not a block diagram, but our sum. So we say F0 minus FC minus FD, and your output is FM. So this is how it is. And we know that V minus W, initial speed versus final speed, is equal to triangle VW. So therefore we say this is V, this is minus W, and this is a triangle VW. So keep in mind that your minus follows this itself. And after we have our equation of balance, we can now write our damping equation, missing equation. So we call it MS. In this case, we have regard everything together, everything total except for the damper. So the formula for the damper is we're going to use FD is equal to RD multiplied by V. So the question would be, how would you know this formula in the first place? Well, that's why it's called missing equation. It means that an equation that was not given to you in the question itself, but it's the equation that you remember solely from pure memory. Is often, sometimes in the exam, the professor may give you a hint, and within the description itself of the question, that he tells you the units of the damper itself, the formula of the damper. So from here, we know FD equals to RdV. So when we rearrange this, we have our GD is equal to FD divided by V, equivalent to RD. So therefore, we know that our transfer function would look something like this. And then hence, we can now make our block diagram. And our block diagram, for example, I think that this question is, I made this question up, so I didn't really assign the input output. I'm not sure if it's appropriate to assign one right now. So if we were to make an equation like let's say we just say that we want an input of F0 and our output of perhaps maybe V triangle VW. So therefore we can say that we start from F0. We draw what we draw here, right? Input of FD, and here is FC, output is FM. So from FM, we know that we had this here. Here. So we say we input FM, we get 1 over M times 1 over S, output V, and we had FD, didn't we? We have FD. FD is basically this one. So we have an input of V and an output of FD. So in here we can draw a block that goes like this, RD, and we connect it like that. So this is your input and then your output here. And when we talk about FC, we have FC right here. And FC, our VC is actually equal to RV. So in here your V, it goes like this. And 1 over C times 1 over S. And your output is FC. But we're not done yet because we have not included this equation of balance. So we write V is the input of W and the output of triangle VW. So in this case, our W was actually equivalent to 0, so you could actually remove this in general. So it means that because our W was 0, so we can say that W is equal to 0, so therefore V is equal to triangle VW. So there's no change. It's like this. So you could remove this and it would be fine.